We ready to go? Okay. And for those of you who are online, basically what I've said was I introduced this, and I will be mainly drawing on these two references. And if you do want to use them and look at them throughout the week, you can find links to them by going to this QR code. Okay, so yeah, let's talk about introduction to quantum Monte Carlo. So just like really with any Monte Carlo method, we need to identify something called a set of configurations and then apply appropriate weights to them. So for typical quantum Monte Carlo calculations that we can do that have no sign problem, it's typically for equilibrium properties. And so what we want is to get the partition function with e to the minus beta h, where beta is inverse temperature. And then we want to break it up into quantities that we can actually compute and treat as weights. So I'll get a little bit more concrete about configurations and weights in a moment. Ultimately, when we do this, when we identify these weights, the point is to compute observables. And so what we are going to do is compute quantities that look like this, which we can do by, if we can identify the observables for each of the configurations. And if we write it like this, we see basically that the observables are going to be distributed according to a probability distribution of the weights for each of these configurations, normalized by the sum of all the weights. And so the idea is, can we find configurations and can we find weights such that we can then select the configurations with this correct probability, because that's what will allow us to compute observables. So to think a bit more concretely, if you think of the classical version of Monte Carlo, where one does the partition function for a spin system, for Ising spin system, for example, what you'd be looking at are spins in just the spatial volume of the system. For a quantum Monte Carlo, what we're doing when we take the trace is we have a summation over all the states, and then typically, in order to compute things, we have some kind of path integral where we have complete sets of states we're going to insert throughout here. And so what we end up with our configurations are configurations that are in space-time rather than only in space. So these are examples of kind of configurations you'd see in different types of quantum Monte Carlos. So this is one for spin systems called stochastic series expansion. And this would be your space, the horizontal axis, and then this is your time. And basically these pieces are like parts of the Hamiltonian. And if you think of the open circles as a spin down and then filled circles as a spin up, it's the Hamiltonian pieces that can change what the spins are. And since it's a trace, the state at the beginning has to match the state at the end. And so for spins, you can often do these things where you really have the physical state of the spin at each time in your path integral. And so this would be an example of one configuration when you're writing the partition function. And then the idea is you have all possible pictures that would look like this. And these are all your configurations in your space. What we're going to see for Fermion, in particular, auxiliary field quantum Monte Carlo as implemented in ALF, is we aren't going to look at the fermions and their states in particular at each time. Instead, we're going to introduce some auxiliary spins and auxiliary fields in general. And so they can also be continuous, but the most common example we'll be looking at is actually like two types of spin ups and spin downs. And so this would be one configuration. We basically have a space-time in these sort of Ising spins. And so this would be an example of one configuration, and we'll be making updates to it according to weights, which will be ultimately to be dependent on the fermion statistics and all of that. Okay, so yeah, we need configurations like what I showed with the spins, selected with the appropriate probability. And so the way we do that, at least for most of the features in ALF, is with a Markov chain, which will be a way for us to move from one configuration to the other. And the idea is if we have two conditions that we can satisfy, the first being ergodicity. So we're going to have a set of rules basically to get from configuration 1 to 2 to 3 and so on. And as long as with these rules, we first have ergodicity, so basically saying for any configuration we select in the space, let's say CA, and we can get to any other, some randomly selected CB. It doesn't have to be immediately, but at some point in the chain, as long as we can get there, we say the system is ergodic. So that's one condition that we need to have. And then the other condition is balance, which has to do with the weights and also the transition probabilities from one configuration to the next in the Markov chain. So as long as you have that basically this summation over configurations I, the weight times the probability of going from CI to a particular K, as long as that's equal to the weight of K and it's ergodic, then one can show the following. Basically, this P you could then write as a matrix. And this could be these correct basically weights according to configurations are like an eigenvector of this matrix with eigenvalue of 1. And if it's ergodic, all the other eigenvalues are less than 1. So then you can show that if you start with a totally wrong set of a wrong set of weights, because at the beginning we don't know what the correct weights for the configurations are, but we just start with the wrong set of weights, but we follow the transition probabilities defined such that this is true, and then we just keep transitioning them, then the limit as we go to infinity is that we would go to the correct set of weights. So that's the idea with it. We are going to follow the chain for long enough, and we call this equilibration. And once we reach the equilibrated state, we are now selecting all configurations with the correct probability that we would like to have. And so then if we think about after they're equilibrated, we could represent these as, say, C star. And then you can compute the observable with these equilibrated configurations. And then if you just add up the observable and take this average, let's say for n of them, then basically through the central limit theorem, we actually will get the correct observable, and the precision of it will go as 1 over root n. And so that's the thing. If we, as long as the problem doesn't scale exponentially, and that's a complication we'll talk about later, the sign problem, you can you really have a rigorous way to get as precise as you would like with these measurements. Okay, and one other thing before moving on, one of the key things, at least for many of the typical applications of this, is that in these Ising spins, that ultimately are auxiliary fields for the fermions, we'll always be doing local transitions. And Johannes is going to talk a little bit about that, but the main point is that that is what is going to make this efficient and time saving. So for example, here, everything is the same, except we propose moving one spin at a time. And then we might accept or reject that, and we'll get into that. But and we go through one time slice at a time as we go through this. Okay. So now I'm going to get a little bit more concrete and talk about the types of Hamiltonians we use and how we write them when we use this auxiliary field software. So the fermionic portions, because we can also do some spins as well, spin interactions, but for the fermions alone, let's just think about that. And we can write them as first a kinetic plus a potential. So the kinetic, we need to have a C dagger TC. And so we can have just some matrix basically connecting the C dagger and C. And then the potential, this is where things are a little bit more restrictive. We need to write this as a sum of terms that are basically written as Hermitian operators squared. So, we have C dagger VC, and this is typically some type of a local term. Maybe it's an on-site term, maybe it's a nearest neighbor term. And the point is then it's squared. Okay. Oh, and I have definitions of these right here. Mhm.
It's not, you said restricted, it's not at all restricted.
Well, I was going to get, it's not that restricted. Yes, that's true. Yes. And yeah, and then okay, so I didn't want to imply it's actually that restrictive, but the point is this is the first step that you need to take in order to do something with the ALF software. But yeah, many interesting interactions can be written in that form. There are plenty of things that don't immediately look like squares to you. These are some of the simplest examples, and certainly when we get into the Hamiltonian classes tomorrow, you'll also see many other things that we can do once we write these as squares. But and there are different ways, different channels that one can decompose these things in. So this is the same Hubbard interaction, but see, with Hamiltonians, you can add a constant, and all that does is shift the energy levels. It doesn't change the physics. So by adding appropriate constants, you can write these operators as various squares. And the point is, too, like I mentioned, this is an on-site interaction. So this is one square, and then you'll have a sum with all the other squares for the other sites too. But it's not like the whole thing is a square, but each of these interaction pieces is. Okay, and why are we doing this? Well, the goal ultimately is to reduce this interacting Hamiltonian into basically a bunch of terms that look like free terms, like free imaginary time evolution terms. And so that's where we're going, because that's what will allow us to actually compute weights for our quantities. Okay, so the next step to do that is going to be to trotterize the system. And so the way we do this is we're going to introduce a discrete time step. So there is going to be a discrete error with this trotterization that goes as delta tau squared. And so it's some time step. We can make it as small as we like, so that delta tau times LT is beta. And so the trace, remember, was E to the minus beta H. We can write it as our T plus V. And then this is the step where we trotterize. And so we have this times L to the T. Now we don't have a discrete error yet because it's still the full Hamiltonian in there. And then it's this, this next piece where we now break it into V and T that we have the error. And then further, we are going to break up our potential term because, like I said, it's the sum of all these different squares for sites. So we're going to break it up into these, they could be site pieces, they could be bond pieces, etc. Okay, some comments. If we do it in this straightforward way, the resulting propagator is not actually Hermitian. And so something that's good to do is to actually use the symmetric decomposition, and that is a feature in the code for most of the Hamiltonians. And then another thing, yeah, this is you can avoid it in certain cases, but these are other methods. And then there's another note that with auxiliary field techniques in particular, there are higher order decompositions, Trotter decompositions that one can do. And Flo has a paper about that if you do want to get this delta t delta t squared smaller than that. Okay. So with that, we're going to move to the Hubbard-Stratonovich. So we have this trotterization, and we have e to the v for each of these vertices or bonds. And now we're going to use this feature of the perfect squares. Okay, yeah, what one can do is if you have something squared, we can basically write this as a Gaussian and be able to rewrite this a squared operator as just an a operator with, say, if we have continuous fields, we could have an integral there over the continuous fields, and that would be exact. But then we can also do Gauss-Hermite quadrature, which allows us to write this in terms of, and these are the four Ising fields that I mentioned earlier. These are where we get basically the spins coming in. So this L can be plus or minus 1, plus or minus 2. And one might say, well, this isn't exact, which it isn't, but the error here is only delta tau to the 4. So compared to the trotter, it's negligible. And so because of that, we can have this nice simple way of writing the a squared in terms of an a using this Hubbard-Stratanovich. And because of that, we're basically at this goal of writing things in terms of all of these pieces are now going to be bilinears rather than having quartic terms in there. And so it's like a bunch of imaginary time evolution of like a free particle type of term. Or hopping, yeah, hopping terms. Oh, we have a question from Sharm.
Oh yeah. So I just want to ask, why this auxiliary field term takes plus and minus 1 and plus and minus 2, the four values.
That's
can
right.
you make that clear? Yeah.
So this is one particular Hubbard-Stratanovich transformation, and I mean for this one, I mean one could do it with more or with fewer, but with the 4, you already have the error down to delta tau to the 4. And now, did you have something about why is it plus or minus? Yeah, is there more to your question about that?
No, I think that's more mathematical. Like if you just expand the sum, one would expect to get the term on the left, right? That's what you meant by this equation, right? But I was
Yeah,
just
one would
wondering,
get
like, yeah,
approximately the term on the left. Yeah.
okay, I see.
Can I make a quick comment?
Okay, to the one, yeah, I just meant that one that I was familiar with was just L taking value plus or minus 1, but I was not aware of taking plus or minus 2 as well. So, okay, maybe this is a higher order prototypization or something.
Can I make a quick comment and can you hear me?
Yes, yes.
Yeah. So the idea here really is to go to higher order, and when you expand both sides and compare the coefficients in the order of delta tau, you can just match these coefficients. And one hint why you have plus and minus 1 and 2 is with the phi's, you ensure that the odd terms vanish. So you never produce a delta tau squared on the right-hand side. And then with having all of these combinations possible, you can ensure this higher conversion. And the two-valued where you only have plus and minus 1 works well for Hubbard interaction, where you make use that the fermionic density operator squared is the fermionic density operator itself. But this equation holds for Hermitian operators A, and it's not specified to the density.
I see. Thank you so much. Yep.
Go ahead.
Boy. Nice throw. There is one thing which we never maybe thought about. This is maybe for more advanced, but are operators always bounded? I mean, this will not work if the operator is not bounded somehow. So did we ever encounter? I never encountered an issue, but we all say perfect is delta tau to the 4th, but what do you say? I mean, especially if you have those projective things, you never, I guess.
Well, I mean,
we had I don't throw so well, so I'll pass it. All right, careful, Disha.
So, I mean, at the end of the day, we often have, at least at high energies, a microscopic model in hand, where you have some sort of short rangeness interactions on a lattice. And there they are bounded, and the projection, as far as I understood, didn't really blow up the energy scale.
I think it's okay.
So at least for most lattice models, when you think of nearest neighbor density interaction, even if it's second nearest neighbor, then you are fine. And I think also the projection from the UV has a limit.
Okay, so then, right, so now I'm just showing the partition function here before we had split up all the vertices for the interactions. And then now we're going to rewrite them using the Hubbard-Stratanovich. So these operators here were, say, were all the squares of bilinears. And now we really have bilinear terms here, just like in the T terms. But what we have that's different is we now have a summation over this gamma, over this the gamma and phi, where gamma are some prefactors that will end up being, they could be at the front of the entire partition function, and then the phi are are dependent on the fields, and they're attached to the operators. Okay, and so then these are the definitions that we have. And so now we really are at our goal of reducing it to these single particle problems. And so now we're at the point where we can figure out how do you actually write this expression for a given set of auxiliary fields. And so that is this next step, which is integrating out the fermions. So there are a couple of different ways one could do this. One could actually stay in the operator formalism, but I'm going to show you how to view this as the path integral. And so for the fermions in particular, when you have a path integral of fermions, you have to use Grassmann numbers. And so I am using the Xi bar and the Xi to represent two types of Grassmann numbers. And so, importantly, these X's refer to a space-time coordinate with both I for the space and tau for the time, imaginary time. And so just like with the operators for fermions, the Grassmann numbers have these anti-commutation properties. And if you square the same Grassmann number, then you get 0. And then for integration, the Grassmann integration is incredibly simple, which makes the derivation of these formulas easier too, because if you integrate a Grassmann number with respect to its measure, then you just get 1. On the other hand, if you just have an integral d psi, but you don't have the corresponding psi there, you get 0. So these are all the integrals that one has for Grassmann numbers. Okay, and so then for the path integral, to actually get there, we introduce the concept of a coherent state, where the state is basically an eigenstate of our C and our C dagger. So C on this state Xi should give the eigenvalue of Xi with the same spatial dimension, and then the same thing with C dagger on this state. And so then it turns out to do that, these are the definitions of the coherent states. And basically using these definitions, one can prove that you can get the identity with this integral involving coherent states. And then one can get the trace of an operator by using this integral. And this is important because this is what allows us to go from what we had a trace of a product of operators that were all these bilinear, exponentiated bilinear operators. And now we can write it as an integral first by using this trace and putting these coherent states on either side of the operator and integrating over them. And then also, now that we've split it up in all of these pieces, we can insert identities at between each of these exponentiated bilinears, and that is what will give us a path integral with an action rather than a Hamiltonian, which is what we began with. So if one does that using the general form that I gave for the V and the T, where the V was in terms of those squares, then this is the action that you get. And as I mentioned, this is in space-time now, whereas the Hamiltonian was only in space. And so we have these tau variables as well connecting the different psi barring psi. And then this piece is where we put our T matrix and then these V connection matrices. And again, what I'm looking at here, because the idea was, can we compute this quantity for a particular auxiliary field? So right now we are integrating over all of the fermion paths, but we are using a particular set of auxiliary fields when we write this. And so ultimately, for the full partition function, we then have additional sum over the auxiliary fields. But when one does this after, inserting the complete sets of states, and then we get this action, we can write this all then in terms of just a psi bar times a matrix times a psi. And so when you have two independent sets of these Grassmann numbers connected by a matrix, the integral, which you can show simply using these relations that you had back here, you can use those and show that what you get is just a determinant of this matrix M. And so then the determinant has this particular form with what we call the B matrices. And the B matrices are defined here in terms of our T and our V. So we have 1 minus delta T times this quantity. And we can take delta T as small as we like. So infinitesimally, we can simply write the B matrix in this way. And so this determinant is of a space-time by space-time matrix, because each of these B blocks is going to be space by space in its dimensions. But we don't ultimately have to use that in order to compute our weights. We don't have to do a full space-time by space-time matrix, because we can further use this Schur's determinant identity, which will allow us to take this original expression, and by identifying blocks with this, we can first rewrite it here so it's one time dimension less effectively, because now we have a product of these two B matrices. And we can just continually iterate this identity until we can write the whole thing as the determinant of 1 plus a product of all of the B matrices like this. And so, as I mentioned, each of the B matrices is spatial by spatial in dimension. So now the full determinant is just spatial by spatial. So the algorithm scaling at the end is going to be beta volume cubed. And this is where the volume cubed comes from, the spatial volume, basically, of this determinant. Now this is nice because it's no longer space-time by space-time. We do pay a price for that from this product. We get mixing of scales. And we have it basically, if we have enough of these B matrices, computing this naively is not stable. So there's a stabilization procedure that Johannes is actually going to discuss on Wednesday. So this can definitely be dealt with. And we have a parameter called wrap that one can modify if you're running into stabilization issues. Okay, so with that in mind, putting it all together and reminding ourselves of the configuration space, all of this ultimately came from, we had that +1, -1, +2, -2 that exists for each one of these vertices for the interaction. And so those are partially baked into the B's here. You can see that because that's the phi that's dependent on the L. L is the +1, -1, +2, -2. And then there you also see it appear in a constant, or yeah, out front, that it's also dependent on the auxiliary fields, a prefactor out front. And so then the configuration space is basically the set of all the L's that one has, and there's going to be number of times number of vertices, basically, where each one of these L's can be plus or minus 1 or 2. And so updates are for these Ising spin degrees of freedom. So going back to this, that's why we are going to be asking, how do we update these spins, and how does the overall weight that I just gave you, that determinant of 1 plus the product of b's, how does that change? Okay. So that was the configuration space, and that was the weights. But ultimately, what we want to do is we want to take measurements in our system. And so how do we do that? So if we go back to the idea of the average observable, well, the average observable, thinking about our auxiliary field configurations, is going to be a sum of all the auxiliary fields with the observable divided by the sum without them. That'll give our average. And we can modify this by multiplying by, basically, if we look at this piece and then this blue part in the denominator, this is just a way of adding 1 to this quantity. But I've written it in this way because if I group these two together, this is basically going to be the observable piece that we want to compute. Because if you notice, this piece here is exactly that probability that I identified earlier. So this is our probability distribution that we want. And then we want a way to compute basically a function that will give us this observable for a particular auxiliary field configuration. And so then for our equilibrated auxiliary fields, this is the thing that we're going to be averaging. Okay, so yeah, we need to be able to compute that. And one can go back to the path integral, but I'm going to discuss a generic observable where we're going to have an equal number of C daggers and Cs, but they could be listed in any order. And so you can think of them as each having their own tau. And so you could put them at different times within the trace. You could also put them all at the same time, and that's called an equal time correlation function. And that's also a type of observable in the code. But you could also put them at different times within this path integral. And so this is a way you could define the operator so that it's at the time that you want, where this is like an imaginary time evolution operator. And we're using, in this definition, we're using a time-ordered definition where if you have these two times, basically this is going to push everything so that the larger time is going to be to the left and the smaller time is going to be to the right. So if they're in the other order, you're going to end up with a minus sign. And also if you have C dagger and C at the same time, then you have a minus sign there too. Okay, so that's our observable form. And we can actually take this directly, correspond the C daggers to psi bars, the C's to psi's. And so here they are with their space-time coordinates. And so in the path integral form, what we want to compute is this path integral. And so this is well known, this is Wick's theorem, but one can take those same identities I mentioned earlier, and what you get is a new type of determinant, and it's also related to this matrix, but basically it's related to the inverse of this matrix, and each of these sets of coordinates are going to connect one of the psi bars to a psi. And so I'm defining this M inverse, in this way with these. So you can rewrite this in terms of a bunch of what are basically 1-point correlators. And so what we want then is to just get what is the inverse of this M matrix. And we know the form of the M matrix. So what we're going to do as well, because this will be useful for later slides, is it's useful to know this quantity is called the Green's function, and it's going to be very important in general to the QMC. But since we know the form of the matrix M explicitly, we can find a form for M inverse, and we can show, we saw earlier that the weights were the determinant of 1 plus the product of B matrices. I mean, this looks somewhat familiar, and I thought I'd show you a relatively fast way, just staying in terms of operators, to see why this is the expression that you get. So this thing changed. There we go. So what we want is, say we want to, is this showing up on the camera, by the way? Okay. And let me know if this needs to be bigger, I guess. I'll try to draw this bigger. But say we have exactly this quantity where we want to get, it's an equal time because they're both located at the same time. We have a set of matrices which are going to be bilinear. So I'm going to say this H is equal to C dagger HC, where these are vectors of the operators, and this H is a matrix now, whereas this H was an operator. You can prove a useful formula, which is that E to this H operator, if we have the C dagger I, you can switch their places in this following way, where you have a sum over all of the Q's. And now we have E to the H operator on this side, but then we also have E to the H matrix QI as an element. And so you can use this formula to basically write this expression in a different way. If you take this C dagger I prime and you commute it past here, and then you commute it all the way around so that you're back at the beginning, what you'll get when you use this formula is minus sum over Q trace E to the H1. This part is the same. And then you have CI and then CQ dagger. And then you get a matrix piece that's a product of all of these. And then this is going to be QI prime, because I commuted the C dagger I prime around. And then I get one additional piece, which is trace of E to the H1 operator, E to the H2 operator, up to E to the HN operator. And so what you have is an equation with two expressions that look pretty similar to each other. And so basically what you can get is a sum over Q trace of the product of these again. CI, CQ dagger, and then you have one plus all the matrix pieces QI prime divided by this normalization piece, which you would like to have. But all of this is just equal to 1. And so then you can just solve for this thing. And so this piece will go over here, and you'll get the inverse of this matrix at that point. And so that's what we have here. So, so this piece will ultimately just be with I, 1 plus E to the H1, E to the H2, E to the HN inverse I prime. And so that's how you can get the equal time Green's function from the operators. And so, yeah, and this is a definition. Johannes will use the G for the Green's function. And so for an equal time, we just put 1 tau to represent the particular time we're at, because the other thing to notice with the B matrices is it's going to matter where these things were located, because that'll determine the order that you see these E to the H's wrapped around. And so if we look at this in terms of the B's in particular, you see that it's exactly at this time tau. That's where you have the split from tau to tau plus 1 in this Green's function. And so the equal time Green's function is the central quantity in the algorithm, as you'll see. And that's basically my part of this morning session. Oh, yeah.
Okay, so I guess the next part of the talk will be done by Johannes Hoffmann from the Max Planck Institute of Complex Systems in Dresden, where he's now a group leader. Emilie, would you take questions now, or shall we just wait for the?
Well, if there are any questions,
any questions for Emilie so far? Yeah.
I didn't get from the beginning. So you're speaking about Fermionic part with Hamiltonian. This is what I saw on your slide.
That's
But
right.
What does it actually mean? So I mean, is it still something else?
This is
only for fermions, right? Anyway.
Fermionic Hamiltonian. This is everything.
But what do you mean that
Say
this Fermionic
you
part
also have,
implies that there is non-Fermionic part.
well, say you have a gauge theory that, or with spin fields that also, like physical spin fields, not auxiliary spin fields. So you could have something like, I mean, this is part of our code. If you have something with, like, say, spins that live on bonds and fermions that live on sites, and maybe there's an interaction between those in the Hamiltonian. So there is some extension to the code that also deals with that, with interacting spins and fermions at that point. But those are additional terms in the Hamiltonian, basically.
Any more questions? If not, maybe we can wait for the questions later. And now welcome Johannes to continue the second part. Thanks, Emilie.
Sure. Oh, let's get this on.
It's already on.
Yeah, it's already on. This is pulled out.
Does this work? Can you guys hear me? Should I put it higher?
I guess maybe somebody online should. Yeah, somebody online.
This is about to fall off. Let's see.
So I can hear you.
Okay, cool. Cool. Thanks. All right. So I'll be continuing for the second part of this introductory lecture today. And Emilie has already shown us how we started with the Trotter decomposition, the Haber-Satonovich transformation, integrating out the fermions so that we derived a purely or a configuration space and classical variables, something that we can handle on a classical computer. And she also gave the formulas on how to extract information, like all sorts of measurements out of it. So the goal of this remaining part is now to tell you a little bit about how single spin flips works. So essentially, see if this works. Yeah. So Emilie had a formula similar to this one, where we have the integration over the auxiliary fields, or potentially bosonic fields, if you think of an Ising bosonic degree of freedom, or if you think of, say, a phonon that you want to couple to your fermions. She derived the probability or the weight that a fermionic determinant is giving, and then how the observables should look like. So, but the remaining question is, how do we sample these configurations phi? And one challenge in this part is that we actually don't know the normalization. So this is one part where the Markov chain algorithm works or helps us, because here we only have to compare the relative weight of two configurations, and the normalization will drop out if I take the ratio between those two weights. So I don't have to know the normalization. And the updating scheme that we want to do, like what are the configurations that we are comparing, is I think I rotated the configuration by 90 degrees. So for me, the imaginary time is on this axis, while space is on the vertical lines. So we start looking at one of these auxiliary fields. We will propose an update, then calculate the acceptance rate according to the Markov chain, propose the next spin update, and then snake through this configuration space all the way from time equals 0 to time equals, well, beta, in this case 10. And afterwards, we will go back, and this will essentially be the algorithm. So this is the configuration equivalent to the drawing that Emilie had in the beginning, where you had this abstract space of configurations, and you started somewhere and you made some change from one configuration to the next. So the configurational changes that we will be doing are precisely these single spin flip updates. So, yes, right. The idea here is, let's first say we have some configuration, L. I might later on use this as an S. So don't be surprised if I switch L from S. But I hope I update the notation to L on the fly. So we have some set of fields L for each operator and for each time slice. Now we pick one specific, or we look at one specific spin that we try to update. So this shall be the ith spin on the tauth time slice. And we want to perform an update where we go from L of I tau to some new value L prime of I tau. So this is the update that we propose. Maybe I can actually go back with one slide. You can think of it as taking the first spin and changing this value. So one quantity that appeared in Emilie's talk is this exponentiated term with the interaction, which depended on the auxiliary field, Li tau. Is there a question? I wasn't sure if there was a question.
No, we're just looking at what it's like to be online. And if you have a better pen, it would be better.
Do I have a better pen?
I'm asking it. But it's more or less okay.
It's okay-ish.
But it's okay, but if there's a better one, I'll tell you.
It's the only one I see here. Sorry? The light? Which one? Light? Tough. Better? Any better online? It's worse?
No, it was relatively better actually.
So better with the light on. This way is better.
Yes.
Yeah, it's relatively better.
Okay. I'll try to write in large letters and complain if I tend to write too small again.
shutters down there.
We could try to shut it down.
Is it the right one? Okay, let's see. Right. And let's
Quick
also,
question.
yes,
Sorry.
please.
Yeah. So you are doing a sequential update. But what's wrong with the global update if I just want to do the global update?
So let me at the moment just quote from practice that if you change a spin, a single spin, the acceptance rate or the relative weight between them is roughly 50%. Now, so if you now try to do changing 10 spins, 10 arbitrary spins in an arbitrary fashion, and you have an acceptance rate of 0.5 to the 10, you end up with a pretty small number. So on average, you would be proposing a lot of spins, spin updates in a cluster that you want to change, but you just never accept them. So the challenge there is to find good updates, updates that have a high likelihood of getting accepted. Yes, so that's the main problem with global updates. So you really need a smart algorithm to find the right spins and the right values to update them too.
Okay. So additionally, I think then one has to find many probabilities at the same time, and that grows exponentially with the system, right? If you just do the global update, then one has to find the exponentially many probabilities as there are exponentially many configurations.
Yes, or in other words of putting it, you are searching for good configurations in an exponentially large space. And if you don't do that in a smart way, you have exponentially many chances of picking the wrong stuff. So you will get exponentially small acceptance rate unless you have an intelligent algorithms to find the good ones. And they are hard to come by. Does it answer?
Yeah, thank you. Yes, thank you so much. Yep.
All right. And also let me specify this to the Hubbard interaction for simplicity of the discussion, but it can in general be written for much more general forms of the interaction. So in Emilie's lecture, there was a gamma L part, the prefactor. Then you had an e to the square root of minus delta tau u of k, the coupling constant of this given vertex. There was the field phi of L, and then it coupled to the operator. And let me now here specify I'm having a Hubbard interaction on the ith side. This is for the tauth time slice. And let's also say we have the density decoupling. So we can make use of the SU2 spin symmetries that these determinants block diagonalize in a matrix for spin up and a matrix for spin down. And here I'm really looking at the up-dimensional part. The whole point is this is now a single fermion operator and there's no hidden matrix structure. Otherwise, we would have to deal with this as a generic matrix, which can be done, but makes the discussion here a little bit more cumbersome with more indices. And you can interpret this piece here, the weight up front, as writing this as an e to the, do I have a minus? Yes, I have a minus. Minus s naught phi, where you, for this purely Hubbard model, fermionic model, where you collect all the terms like these prefactors that do not depend on your fermionic operator. But coming back to your question from before, here you could take a step back and say, let's define the operator like this. Let's define the field phi, for example, as a continuous variable, which I don't interpret as an auxiliary field, but which I take, for example, as the displacement of a phonon. And in this case, I could have a bosonic phonon term that couples to fermions. You could also couple to the spin and think of this as a spin fluctuations in the z direction. you could also say that this field phi is explicitly an Ising variable, so I'm coupling an Ising degree of freedoms to fermions. And all the dynamics that you then still have in this bosonic degree of freedom will be residing in this action S naught. And when we will compare, when we will be comparing two different configurations, you will have to provide the change in this S naught function determined either purely by these gamma terms, which is then taken care of automatically for Hubbard-like interactions for these perfect squares. For all the other degrees of freedom, you can provide the dynamics of themselves through this S naught. I hope this answers your question, what the missing part is. Oh. That feels weird. I hope people can still hear me and I'm not yelling in the microphone right now. All right, where did I want to go? Okay, so when I do this change, when one specific variable changes from L to L prime, essentially the term that changes, aside from this S naught, is the operator that I have written out here. So if I look at the product of all the B's, so let me organize them right now already in this way. To B1, and then from BL trot all the way to B tau plus 1. This is the formula Emilie left us with for the Green's function on the last slide. And also 1 plus this expression, more precisely, let me write it like this, 1 plus this expression. The determinant of this will give the proportionality of the weight. So we changed this field, which implies that if I look into this B matrix, there is this e to the v for the field Li tau times then all the other stuff. And this is the term that changes. And I want to formulate the change as, let me write this explicitly, e to the v, this is supposed to be an L prime of I tau, shall be equal to the identity plus v to the new one, L1, e to the minus v, the old one. Maybe let me write this more clearly. The first one has a prime, the second one doesn't. Minus 1 times the old e to the v L. And there is a minus 1 missing here. And the point of this parametrization, on one hand, the minus 1 eliminates this one. The minus e to the minus v will essentially remove the term that I have already present in the product of all the b's. And this term will insert the new one, precisely the fraction that I have. But I have written it in such a way that I get a delta, or I can introduce a delta, which I define like this. And now remembering that this v is very local. There is one side where I'm coupling the field to. So on the exponential parts of all of them, I have the identity. So this part, the exponential part, is a matrix which has a lot of ones on the diagonal. And then it has precisely one entry where I have these field configurations. So there will be some prefactor, some number prefactor, and then the essential part is there will be phi of L minus phi, sorry, L prime and L. And then additional ones on the diagonal. So if I subtract this, this will become a very sparse matrix where all of the identity, all of the entries vanish, but 1 point. And we will be able to make use of this. So why did I go through all of that? Let's not forget that at the end of the day, when we want to do these updates, we have to adjust the probability transition rate according to the relative weight. So I have to compare the weight of the new configuration with the weight of the old configuration. So for this, let me introduce B L prime beta 0 as an expression for the product of all the B's, where I start with tau 0, so the B1 will be on the right side, going all the way to beta trot. So for this, and I have explicitly that this is the product of the B's for the new configuration after the update. And I can write this now as the B of the old configuration L without prime from beta to tau. This is where I changed the operator inside this chain of products. And this changes specifically to 1 plus delta. And then I have all the other terms, again, given by the old configuration L, that remain for the time interval from tau to 0. And this implies now from this relation that the determinant of the new configuration divided by the determinant of the old configuration will be 1 plus BL beta tau, 1 plus delta, BL from tau to 0. And this gets divided by the determinant of 1 plus the old BL again, from beta all the way to 0. So I do not have this insertion here. And I won't be going through all the steps of the derivation, but it's actually quite straightforward to see that if I look at this ratio, I can write this as the determinant of the identity plus this changing matrix delta times BL from tau 0, 1 plus BL beta 0 inverse BL from beta to tau. And this 1 plus B inverse is essentially the determinant that I'm dividing by, and then otherwise I have used the cyclicity of this trace and eliminated once this, because the factor with the one that I have here is precisely canceled by this term. And then with a little bit more of shuffling things around, I can write this as the determinant of 1 plus this matrix delta, the identity minus the identity plus BL of tau 0 to B beta tau. And this gets inverted. And now I have to close this parenthesis and the part of the determinant. And this expression is precisely the expression that Emilie left you with. This is the Green's function of the old configurations L at the time tau. So the formula that we have arrived at, if I want to compare the determinants of the weight stemming from the Fermion trace, that this whole expression is equal to the determinant of the identity plus this delta matrix, which is very sparse for local operators, times the Green's function from the old configuration. So this is underlining the statement that when you know the Green's function, you know how to compare two weights between configuration that changed on one operator. And this is also the quantity that with Wick's theorem will give you the measurements, the observables that you want to determine. Okay, I have 14 more minutes. So, okay, so this quantity tells us how important two similar configurations are. What we will now take, and let's say this is part of the rate. Do I have this on the next slide? Yes. So the determinant is taking part of the fermionic, is taking care of the fermionic contribution. This is the change in the weight that can come from phi's that are bosonic, extra bosonic degrees of freedoms, or encode the gamma prefactors. So this number or this ratio here will then determine the probability in the Markov chain and how we transition between them. And after I've done one update, after I've calculated the relative weight, I calculated the probability, whether I should accept this or not. Then let's say I accept this, move this update. Now I have to change the Green's function because the Green's function will determine, again, the acceptance probability for the next proposal that I have if I transition from the first auxiliary field to the second. And let me be a little bit briefer here. So the new Green's function S, L prime, can be written as 1 plus, and I'm again making use of this quantity 1 plus delta that I introduced. This is the change of the B term. So I have the B, this is now without the prime, so this is the old configuration of tau to 0, BL beta to tau inverse. And let me write it, this one in this form. So I want to reshuffle the structure of these things. And what you can typically do is you can pull B factors in and out from the front and back, and you just have to make sure how does the inversion of a matrix deal with this. So I want to write this as BL inverse from beta tau times the identity plus BL beta tau 1 plus delta BL tau 0. This gets inverted. And then I have a BL beta tau. And to convince yourself that this is the same one, this matrix enters from the front as an inverse, removes this part. So I'm left with this part of this calculation here. And this piece enters from the back, but not an inverse. So it's generating this term that I have here at the back, and which is missing here. And both of them meet at the identity and are relative inverses to each other. So continuing this, I have BL inverse beta tau 1 plus BL beta tau. So I'm collecting the one term, BL tau 0, And then the term that is missing is the term that has a delta. And now I'm using the sparseness of delta, that there is only one element different from 0. So I'm able to write this part here as an outer product between two vectors u and v. I need the inverse. And I still am left with BL beta tau. And u is given by, or defined by, BL beta tau times delta. And this is, if I think of this as the ith component, I have to take the ith component. Sorry. The x component, I have to take the xi element, and keep in mind that this is the delta for a change on position I. So this is the only number where delta is not vanishing. While v and the x component of v is just bs tau 0, and then the matrix components ix. Now I can make use of the Sherman-Morrison formula, and I'm not going through the details of these linear algebra transformations, but I can show that this is then given by the old Green's function minus the old Green's function at time tau, so this is all at time tau, times delta 1 minus the old Green's function at time tau. And here I divide this by 1 plus delta 1 minus L of tau. And since this matrix is so sparse, this is just a number and I can divide this. Otherwise, we have to be a little bit more careful with the precise order of this and write this as an inverse of a matrix as a factor in there. So what we have achieved now is we know how to compare two configurations that change by precisely one spin that I flipped. And we know how to change the Green's function to keep going in this chain. Yes, so this is what I've just discussed. And once I'm done on the first time slice, I transition to the next time slice, where I also have to cycle through. So when I want to progress to the next time slice, beta of tau plus 1, I have to pull this beta tau plus 1 from the back and bring it up front. So this is precisely this multiplication routine that we have to propagate the Green's function from one time slice to the next. And then we can just keep going, update the auxiliary fields with this following the same formula all the way until you hit the last time slice, where we turn back. And now the propagation of the Green's function is, of course, in the opposite time direction. So the formulas is slightly different, because now instead of moving a factor from the back to the front, we have to move a factor from the front to the back. 5 minutes. Okay. So, right. This was a crash course through the single spin flip updates with the important formulas on the blackboard, or whiteboard, I should say. So let me use the last 5 minutes to say a few words about the ALF algorithm, the software package itself. Because one of the design principles that we had in mind is we wanted to separate all the details that you need and that you need to take care of when you do the Metropolis Monte Carlo from the Hamiltonian, so that it's easy to take out one specific Hamiltonian and replace it by another, and you use the same updating routines for a new model. And the model is defined by giving these interaction matrices. They will determine the interactions. I have to specify the hopping matrix, which will give the kinetic term of the electrons. What is missing? What is happening here? So, and also you need to provide the function S naught if you select fermion boson models. Right. And then there will be a routine where you can calculate the observables. So these are the three things that you will have to specify. And I think you will be showing and seeing this throughout the rest of the week. There will be Hamiltonian modules. The Hamiltonian module will have a member function hamset. And the purpose of this hamset is to define your interaction terms V and your hopping matrices T. There is also this function S naught, which will define the dynamics of the bosonic degrees of freedom if you go beyond just quartic fermion interactions with auxiliary fields. And there will be two functions observables, obser and obser T, for equal time and time displaced Green's functions. There is this, all of this can be found in the subdirectory proc and then the subdirectory Hamiltonians, where you specify your different Hamiltonians, your different models, and define how they look like. Yeah, for those who are interested in, I think inside proc, there is a routine called upgrade, where the single spin flip is implemented. Yeah. One thing that I should say, and that Emilie also already hinted at, is that these B matrices is a product of exponentiated matrices. So we start mixing exponentially large and exponentially small scales. And this can cause numerical instabilities, where just I don't represent the exponentially large and small scales correctly anymore. So after a given number of time slices, and you can specify this number by n rep, this sweeping routine will come to or will take a quick break to recalculate the Green's function and to ensure that both the product of these B matrices is stable and also the calculated Green's function is stable and didn't accumulate numerical errors from continuously doing Sherman-Morrison-like updates to the Green's function. And I think it's not progressing anymore. What's happening? Maybe this is already the last slide, because I think this should be done. The only thing that I want to mention is you will get to know the info file, which is produced when you run ALF, and this will record the precision of the Green's function by comparing the Green's function that is propagated through Sherman-Morrison to the Green's function that is recalculated from the B matrices directly. And this is something to keep an eye out for when you run the simulations, that it didn't get unstable. And if the deviations are too large, nrep is the parameter that you should adapt accordingly. And I think that would be the end of my presentation. Sorry? Yeah.
So
Questions?
before we take questions, maybe it's good to ask our online participants if this was visible after we pulled the shutters down, and it's okay. Maybe then
It's too late.
is this, yeah, but maybe we can take the feedback for the next session. So anyone online, would you like to tell us if the boardwork was visible finally?
The subscripts are a bit small, but overall it's visible, in my opinion.
That can
Yeah,
be worked
it is
with.
visible.
Okay, thank you very much. So now let's take questions for Johannes and also Emilie, I guess. Yeah. So maybe I can start actually. So,
Sure.
In the scheme of updating single spin flip by single spin flip, is it important the order in which you'd have to update the single spins in the same time slice? Is the snaking order important, or is it just convenient to draw it like this? Would it work if I just randomly do it in a single time slice and then go to the next one? Is there an advantage? Yeah.
Yes and no. In principle, you could randomly select a spin that you want to update, and you don't snake through at all.
Yeah.
The question then is, what you have to do is you have to cut the product of all these exponentials in the B matrices at precisely the position where you want to update. In some cases, you are lucky, like with the Hubbard interaction, that all the different terms of the interaction commute. So then you get a little bit of leeway on where you place yourself. But in principle, you would want to isolate the interaction vertex at the end of this product, because then you know exactly that this, where is this? Where this 1 plus delta term shows up inside the chain. So you would have to calculate this Green's function for the position from scratch. And this is actually a fairly expensive routine. And you have to worry about the stabilization and everything. So it's much more efficient to reuse the Green's function that you have and then propagate the Green's function along. And it's a long way to propagate the Green's function from 0 to the random time you picked if you want to do the update at a random time.
But what if at a,
where you really have to trotterize, like the V term. If you just had a U, you could just stay at this slice and then do any of the sites there where it's updated.
So for the Hubbard interaction, you could, but for the ALF, we do not assume that different V terms on the same time slice commute.
Yeah.
So with ALF, you will move to exactly the right spot for your update. There is a global tau update, which can do these propagations back and forth for you.
this is, you're saying there's different V terms in the same time slice, which might have an intrinsic ordering, which we don't want to mess up with when you put it in. when you trot it.
In general, yes, there
Yes,
can
yes.
be. And I think Fakir has a comment on this.
Oh, good gosh. Oh my God.
Emilie, I mean, you're a great physicist, but you have to learn how to throw. I mean, we have to be careful of computers. No, here's an exercise which we could do. We could just have fun. Just program something and do a sequential, and then reprogram it by doing it random in the time slice by using the global tau. And you will see, I think Joao here knows how bad it will become, because you have to place your Green's function always at the same place. You have to copy things, etc. And this is a bottleneck. This is not a very well done thing in the ALF for the moment, and you could see it right away. So this could be one thing we could think of as an exercise if one wants to see how bad. Well, may be fun to do. I don't know. Let me show you how to throw, Emilie.
Yeah.
So more questions for, yeah.
Hi, somewhat related. So, what about if I don't like follow this snake, meaning at the time slice 1, I go sequential from side 1 to n, but at the time 2, it's not from n to 1, but still 1 to n and 3. So this should be okay, right?
Very good catch. I was a little bit sloppy in this drawing. We actually always go from 1 to n, from 1 to n, and from 1 to n on every time slice. The more important part really is that the Green's function that you use to determine the weight and that you then update is in sync with the position where you cut the operator chain into halves, and where you know that the change will be given by this 1 plus delta. So the synchronization is the most important. Otherwise, you get the wrong algorithm. Now it depends on you how you organize things and how you ensure that they are synced up.
Okay.
I
There
do think that just as a note, there's a separate question of, what works for efficient code versus what works in general. It is true we could randomly pick sites from any of the time and any of the space, and that would work. In fact, if you do random time and space, it actually satisfies detailed balance at that point. The snake, or going linearly in time, satisfies balance, which is all we need for it to work, and then it's much more efficient. We get this beta scale, linear and beta scaling, and so that's important for that. But in principle, one could select anything and it would still be.
Okay, thanks.
Okay, so as I was wondering, if you propagate your Green's function, of course, at some point you will get some deviation. And if you're in the phase where you want to define your nrep, and you start, I don't know, a simulation, are there measures taken in ALF that you would get an error message if the deviation is too large?
Yeah, and I'm sure we'll see this in some of the tutorials, but there's an info file that actually tells you, it computes the Green's function in two different ways and tells you the deviation between those two computations. And basically, if it's stable, you'll see something 10 to the minus 10 or something. But once it becomes unstable, you can get things of order 1 and whatnot. So that, and then also, at some point the code does crash. Yeah. But you should always check the info file anyway and make sure that your nrap is sufficiently low to have.
Yeah, and I was also wondering, so let's say you thought you picked a good nrep and it worked reasonably well. Is it, so from experience, is it possible that things can go terribly wrong during the simulation? Or if you pick an nrep that is stable, that's shown to be stable in the beginning, will it also be stable in the rest of the calculation?
So I don't think I have had simulations where stability was a trouble, but I have not had simulations where I could have a code run for, let's say, a week and nrep of, I don't know, 10 was fine. And I had a stability up to, let's say, 10 to the minus 6. Yeah, let's say 10 to the minus 6. And then I continued after a week for another day, and suddenly the stability went up to, I don't know, 1, an order 1 number. This has not happened to me. If something like this happens, it's more likely that there is some sort of bug or issue or corrupted file when you restart. The code will terminate, I think, when the Green's function deviates by order 1 or order 10. Order 10, because the argument was that a Green's function should be typically an order 1 number or smaller. And the smaller part depends now on your correlation length in the system, in time and space and all of this. But at least the on-site measurements, like where you would measure the density of a fermion, this should be an order 1 number. So if you get a deviation of order 10, this is definitely wrong, and there's no discussion about this. The trickier part is sometimes it can be challenging to make the code run stable. And now it depends on you what you are willing to accept. And should we draw the boundary at 10 to the minus 3? For some simulations, this would already be an error that is too large, and you can easily push it down to 10 to the minus 7. So you would walk away with 10 to the minus 7. But if you can't push it down, then you have to really think carefully, what does it mean if I get the Green's function wrong by 10 to the minus 3, and which kind of results are still somewhat okay and which are maybe not?
Yeah, that would be my last question, if it's okay. Yeah. How do you actually account now this deviation into the actual error you get in the end? Is it much smaller than the error you get from the trotter decomposition, or?
So
is it when is it necessary to start to account for it?
Yes. So if you think about the energy as an observable, then the energy is something that you can estimate up to like 1% error, or maybe even more precise. Now, if you have a Green's function and the maximal instability is 10 to the minus 3, which could, for example, mean that as part of the energy, you want to calculate the Hubbard interaction. And part of this is you will have to calculate the density observable. And this should measure the local density, and this is 0.5. So we don't know this, but let's assume that the largest deviation of 10 to the minus 3 was actually measured or detected for this a half factor of the Green's function on site. Then you know that the Green's function that went into the calculation of the observable is wrong by 10 to the minus 3. So you should expect that the potential energy probably has also a relative error of 10 to the minus 3, which is 1%. Then the deviation that you get from the unstable Green's function R is large, or even larger than your Trotter error. So I would feel very uncomfortable if I find deviations of 10 to the minus 3. I try to aim maybe 10 to the minus 5 or less. And if I can get less, I'm happy. Maybe Fakia or somebody else who's running a lot also has impressions on what is acceptable for Green's function stability and where are the limits. It's a tough question, I think.
But so there's a question. There are two measures. There's the mean and the maximum. So you were talking about the maximum or the mean, right? So if you're talking, I always look at the mean because I average over all my things. So if the mean is 10 to the minus 6, I'm happy.
Yeah.
Even if I have a maximum of 1, I will be tolerant of that if the mean is minus 10 to the minus 6.
Yeah.
But it's nicer to have them very low, both, right?
Yeah.
Of course.
And for this, it really depends on how easy is it to push them to low numbers. And there is one thing that, so yeah, actually we have this here on the board. When Emilie showed the Hubbard interaction, she showed the density and the spin decoupling. And they differ by a relative sign in U. So when you take the square root, one of these decoupling channels will always have a real prefactor. The other one will have an imaginary prefactor. Now, when you think of what this means, if this prefactor is imaginary, this matrix turns into a unitary. And unitary preserve the angle and the norm. They just do rotations. And one of the trouble that I will explain later is that these matrices are generically not unitaries. So they can distort angles and norms. And in the most extreme case, it can look like that two columns became linearly dependent because you can't resolve the angle anymore. And then the determinant becomes ill-defined. So it will make a huge difference if this prefactor is imaginary or real on the stability, because in one case, you don't introduce instabilities through the interaction. In the other case, you do. So one is harder, the other one is less hard to stabilize. So it really depends on the model. It depends on the formulation of the auxiliary field that you introduced, how hard it is to make it stable or not unstable. So there will be a trade-off.
Okay, thank you.
Are there any more? Yeah. Just a moment, can I just get back? Sorry, just so that the online participants also hear you.
So maybe I missed this. This decoupling, is it independent of the sign of the interaction? So let me continue.
So there's always a relative sign in the Hubbard decoupling, depending or in the Hubbard interaction, depending on whether you take a density or a spin decoupling. The effective U that enters will always have a sign change or a relative sign difference between spin and density decoupling. So there will always be a relative real versus imaginary decoupling, independent of the sign, like of U itself. But now do I get this right out of my head? I don't think so. So let me not guess. But for the repulsive Hubbard interaction, one is real, the other decoupling is imaginary. And if you switch to attractive, the decoupling flip their relative, flip the roles.
And is there like an energy scale start to be affected depending on the sign of the interaction?
That's a tricky question that one can't answer in general.
Okay.
There is something that I learned with experience is when you look at the repulsive Hubbard model, you have low-lying spin degrees of freedom, and the low energy physics is dominated by spin physics, not by charge fluctuations. So when you have if you wanted to do a mean field theory, this is why you would pick a spin decoupling to do mean field. For the auxiliary field, this is the bad decoupling. You want to avoid the one where you would naturally do the mean field, because in the mean field, you would generate a Mexican head potential if there is symmetry breaking. And then the algorithm will always also have to flip between the different ground states of the Mexican head. And this can be challenging. So if you have the option to choose a different decoupling channel, for example, the density, then the density represents the high energy excitation, physical excitations. So the effective potential that I would expect for the auxiliary fields is much more Gaussian, much more nicer. There's no double well Mexican head structure in those. So the autocorrelation times I would expect shorter and the sampling to be, from that perspective, more efficient if I use the density decoupling for repulsive interactions and the spin decoupling for attractive Hubbard interactions. But this is a statement specific to Hubbard.
Okay.
And that double well structures is related to autocorrelations. This is often the case.
Would you
Please-
go?
please, one more. So regarding stabilization, is there anything else you need to touch apart from NRAP? Because I could imagine a case where your NRAP is really small, then it becomes computationally expensive because you have to complete the Green's function each time.
Remind me of the question in 2 days when I will speak
Okay.
about stabilization. But yes, I mean, making NRAP smaller should lead to more stable simulations. The problem is at this point that the smallest number you can reasonably choose is 1. Because the code at this point does not allow stabilizations within one time slice, so the highest frequency is after every time slice. There are cases where even then the simulation would not be stable. So you have to modify the energy scales produced on a single time slice. And the way to do this would be to reduce the delta tau. But this can come with other issues itself. So you also don't want to have too small of a delta tau. Because you have more fields to sample. There are you can run into autocorrelation issues and yeah. So let me leave it with this.
Any more questions?
Can I ask 2 questions?
Yeah, sure.
Yeah, one question is how do you update the spin? I think now for each L you could have 4 values. How do you determine which value it goes to?
So we always propose a change. So it can actually only go to the 3 other options, not the one that
Right.
it is.
Right.
And at this point, Bakia, please correct me if I'm wrong, but I think we have essentially a 1/3 chance for each of them. So we essentially
so
roll the
just-
dice and pick one of the 3 others with equal probability to update.
I see.
Yeah. Yeah. It might be worth thinking about bringing in a probability for this because the larger L value have a smaller prefactor, but anyways.
I see. And the other question I have is in your derivation, you said you use the SU2 symmetry. And what if I have spin orbit coupling that so that the model no longer have this symmetry?
Yes. So I used the SU2 symmetry, or maybe I should have been more precise, the U1 spin rotation symmetry around the C-axis, so that I can ensure that the spin up determinant or that this M matrix, as Emilie introduced it, block diagonalizes in a matrix for spin up and a second matrix for spin down. And if I calculate the determinant of such a block diagonal matrix, it's the determinants of the 2 blocks. And here I was looking at one of the blocks, which actually still applies for the spin decoupling of the Hubbard interaction. But the main reason why I did this is for the blackboard, I didn't want, or whiteboard, I didn't want to introduce even more indices If I have a bigger operator where the internal dimension of the operator is larger, think, for example, about a hopping term that you have an auxiliary field coupling to a hopping. Then this change delta is not just a number, but it's a 2x2 matrix or a 4x4 matrix. So you can then go through the formulas in a very similar fashion. You just have to keep in mind that these are always matrices. And for example, for the Green's function, when I write it like this, I was here simply dividing by a number. This is a little bit more complicated if this number is actually a matrix and I have to take its inverse, because then the position in here matters as well. But ALF is not assuming that this delta is a single number. It rather deals with it as a matrix. So it was just a simplification for the discussion here.
I see. Thank you.
I would like to maybe ask a question about Emilie's part of the talk. So you mentioned about the trotted decomposition and how it's good to have the symmetric trotted
Right.
decomposition, because if you don't do it, the propagator is not Hermitian.
Yes, that's right.
And then would you maybe tell us a little bit about why do we care about the propagator being Hermitian? What goes wrong if we, why is it an important thing? Or is it easy to?
Yeah, I think maybe somebody else is better to comment on this. If Fokker, you want.
Good. So I think it's so, there's a whole domain of non-Hermitian, Hamiltonians, etc. And especially there are many problems. So first question is, if you have a non-Hermitian Hamiltonian, then the energy spectrum could have an imaginary part. And your Green's function, instead of decaying exponentially, can start oscillating. And then you plug this into Mach n and it will crash, right? I mean, so these are obvious problems which we have, and there are some examples in the documentation. And then there's the other question, which is non-trivial, and there's a paper on that, which I thought rather interesting, is if you have a quantum critical point and you break a symmetry, you break the hermiticity of the Hamiltonian, will the exponents remain the same? Is it a relevant perturbation or not? It's not a trivial question. There's a PRL on that. They say it's not relevant for Gauss-Neveu. I think I don't remember exactly the details, but these are all symmetries you break, and then you don't really know where you're going, right? Right. So if they're small, it's okay, maybe. Even if they're relevant and they're small at a critical point, you may not get to the lattice sizes where they become dominant and you see something, but it's tricky, right? Is that okay?
Yeah, thanks.
I would also like to add a comment to this question, because I think this was like where you were looking at physics in the imaginary terms. Is it a relevant perturbation?
Yeah.
Here you could also ask the question, what happens if you have a perfectly Hermitian Hamiltonian and your your trotter decomposition breaks it?
Exactly.
And one thing that I think happened to some of us in the past is, if you look at the spin susceptibility or the density susceptibility, the density specifically is the expectation value of a Hermitian operator that gets squared. And this expectation value definitely has to be positive. There's no way around it from physics. If you have this imaginary part generated from the trotter decomposition, then this statement does not hold true anymore. So you can have these oscillations in the Green's function that Fakir mentioned, and they could show up as negative susceptibilities, which by definition can't be negative. So this would be a trotter error that shows up in this way.
Wait a minute. Careful.
They could right now make use of this symmetric decomposition or something like this. Make use of this symmetric decomposition.
So the question was if we can make use of the symmetric decomposition, and in many cases, yes.
I mean, does the code make use of this right now?
Yes. So if you look, for example, at the Hubbard model that is implemented in ALF for all the different lattices, or for most of the different lattices, I'm not sure if there is one exception. then you can turn a Boolean variable called sim on, and this introduces the symmetric decomposition.
I will also comment on the functionality available tomorrow on when you can do that or not.
Okay, so I guess if there are no more questions, either offline or online, we can bring this session to the close and thank both speakers once again for taking the presentation.